Hello, everyone. So we are dealing with functions of two variables and more than two variables. And we have discussed about chain rule of derivatives, Leibniz formula, etc., etc. Now we will be dealing with maxima and minima of function of two variables. And in this class, I would like to derive necessary conditions for maxima, minima of a function of two variables. And we will be using chain rule of derivatives for that. So let us get an insight about how maxima and minima of a two variable function looks like, how to deal with it. So let us start. So we all have seen that whenever we have a function of one variable geometrically, let us see what is happening. So suppose you have a function of one variable, y is a function of one variable. And suppose you have a function like this, okay? So you can see that there are peaks and dips. So these cross represents the peaks, okay? And these circles represent the dips, okay? Now these crosses are known as the points of local maxima, and these dips are known as the points of local minima. Local or relative is the word, okay? Now why it is called local? Because if I look at this particular point, this is a maxima in its neighborhood. ये अपने आजू बाजू के एरिया में maximum है. It is the boss of its locality. That is what I'm saying. Otherwise, there's a bigger boss sitting, then there's even a bigger boss sitting, and so on. That is why these points are known as local maxima. Again, if you look at these dips, these are known as local or relative minima because they are taking the least value in their neighborhood. अपने पड़ोस में ये सबसे कम value ले रही है. That is why these are known as local or relative minima. Now, what is the beauty of these points? अगर आप ध्यान से देखें, if you look at a maxima, before the maxima, the rate of change of the function is, positive. That means dy by dx is positive, and after dy by dx is negative. That means maxima is that point at which the derivative should be zero. Because I was positive, 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 suddenly I became negative. That means in between I have to become zero. Okay, so we have positive, then we are less positive, then we are less positive, then we are zero, then we are negative, and so on. Similarly, if you look at these points of dips, okay, at these dips, what is happening is that your derivative before the dip is negative, and after the dip, it is positive. So at the dip, what will be happening? Y dash was positive. So what was the necessary condition for maxima minima, local maxima minima of a function of one variable? The necessary condition was dy by dx is equal to 0 or f dash x is equal to 0, where f was a function of two variables. Okay. Now we are going to do something like this with function of two variables. Okay. This was a function of one variable. So now let us see how that works. So now let us talk about a function of two variables. If we talk about a function of two variables, just look at this diagram over here. Whenever we are drawing diagram of a function of two variables, the diagram is going to be a surface in three-dimension area. So maxima point is something like, suppose I'm wearing a cap, okay? So the highest point on the cap is the maxima, okay? And suppose I'm carrying a bowl, the lowest point on the bowl is the minima. So that is how a surface will look like in 3D, and that is what is meant by maxima or minima. Okay, now let us try to derive the necessary condition. So for example, if z is a function of two variables, okay, then suppose I want to, differentiate z with respect to some variable, d. So I want to calculate the total differential. So the total differential with respect to any variable, suppose it is with respect to t. So we already knew that it is the partial derivative of x, of f with respect to x, then dx by dt, and then partial derivative of f with respect to y, and then dy by dt by chain rule. Okay, that means I can write my total differential as fx dx plus fy dy. Or if we talk about these particular notations that we're dealing with in this particular case, so that is f1 prime x plus f2 prime dy. Okay, now I already told you that for maxima minima, we want the first derivative to be zero, and that should hold for a second or a function of two variables. So that means for local maxima or local minima, what should happen? My dz by dt should be equal to 0. Okay. What does it mean? It means that my fx dx by dt and fy dy by dt is equal to 0. Okay. This means that my fx should be equal to 0 and my fy should be equal to 0, because this should be happening for all x and all y. Now, when is this possible? This is only possible when fx and fy are identically 0. So what is the first order condition for a function of two variables to have a local maxima or minima or relative maxima or minima? The first order condition is that the partial derivative with respect to x and the partial derivative with respect to y should be equal to 0. This is similar to the case dealt in the function of one variables. Okay. Now, this is a necessary condition. Necessary condition means अगर हमारे function का किसी point पे local maxima या local minima है, तो उसमें first order partial derivative उस point पे 0 होने ही पड़ेंगे. If the first order partial derivatives are not equal to 0, then we will not be having a local maxima or a local minima. Now, always remember that whenever I'm talking about local maxima or local minima of a function, I'm talking about the interior points. Okay, so for example, if my domain is from A to B, like in 1D, So if my domain is closed interval AB, I will always be looking at these interior points. Okay, so I will never be looking at the endpoints. At endpoints, the derivatives have a different story that will be discussed later. But the points at which maxima or minima will occur will be the interior point of the domain. Likewise, in case of 2D functions also, these points of local maxima or minima are occurring at interior points of the domain, not on the boundaries of the domain. Okay, so these are the necessary condition for maxima or minima, and these points are known as stationary or turning points. Okay, why these are called stationary points? These are called stationary points because rate of change becomes zero. That means after this there should be, before this and after this there were the rates of change were positive, negative or something, but at these particular point everything becomes stationary. So everything becomes stationary at the points of local maxima or local minima. So this is all about necessary conditions for a function of two variables to have a local maxima or minima. And let us try to attend some questions now, and we will be attending the questions only from necessary conditions point of view. Sufficient conditions will be later. Okay, so let us look at this example 17.1 from Sader and Hammond. A firm produces two types of goods or commodity A and B. The daily cost of producing X units of A and Y units of B is this. Suppose that the firm sells all its output at a price of 15 for A and 9 for B. Find the production levels that will maximize the profit. Okay, so before understanding the problem, understand what is profit function. So profit function is always the cost function minus the revenue. The revenue function minus the cost function. Because for profit, I want my revenue to be greater than cost function. Okay, now cost function is given to us, and what is the revenue function? Okay, the selling price for A is 15 per unit. So 15x, x is the number of units of A. And the selling price for B is 9 per unit. So the selling price total will be 9y. So what is my profit function? My profit function is 15x plus 9y minus the cost function. So what is my cost function? 0.04x square plus 0.01xy plus 0.01y square plus 4x plus 2y plus 500. Okay, so if we collect all the like terms, let's try to have an expression. So first we collect the terms of x square. So there is only one term of x square. Okay, then collect the term of xy. Then collect the term of y square. Then 4x, and when subtracted from 15x is 11x. And then 2y when subtracted from 9y is 7y. And then minus 500. Okay, this is my profit function. So we have just studied the necessary condition for maxima and minima. So we want to have maximum profit. So let us have the necessary condition. So the necessary condition is that the partial derivative with respect to x should be 0 and partial derivative with respect to y should be 0. So let us calculate the partial derivative with respect to x. So that is minus 0.08x, okay, minus 0.01y plus 11, okay. And then, yes, and then if you look at partial derivative with respect to y, so it will be minus 0.01x minus 0.02y, okay, plus 7. Okay, so I want these both the things to be 0. So I'll be getting simultaneous equation. All right, so my first simultaneous equation is 0.08x plus 0.01y is equal to 11. Second is 0.01x plus 0.02y equals to 7. Okay, let us multiply the first equation by 2 and then subtract. So 0.08 into 2 is 0.16 minus 0.01 x. Y will be going away, 22 minus 7. So 0.15 x will be 15. So x will be 15 upon 0.15. So 1500 divided by 15. So x will be 100. Okay, now let us calculate the value of y. So we can use any of these equations. So let me use this particular equation, the first one. So 0.08 into 100 plus 0.01y equals to 11. This implies that 8 plus 0.01y equals to 11. So 0.01y equals to 3. So y will be equal to 3 upon 0.01. So y will be equal to 300. That means when the quantity of A is 100 and the quantity of B is 300, I am getting a turning value. So now this turning value can be a maximum, can be a minimum. We will not decide that right now. But since the question is asking about maximum minima, so of course they have given you a question to calculate the maximum minimum, but right now we don't know the sufficient conditions. So as per necessary condition, the point at which local maxima or minima occurs will be for x equals to 100 and y equals to 300. And how did we calculate that? We used the necessary conditions that the first order partial derivatives with respect to x and with respect to y both should be equal to 0. Okay, now let us try to do one more examples. Example 17.2. Suppose that y equals to fkn is a production function with k as the capital input and l as the labor input. Let the price per unit of output be p. Let the cost of rental per unit be capital R. And let the price per unit of labor be W. Where P, R, W are all positive. The profit from producing and selling is then this. Of course, let us see. So pi KL is the profit function. Okay, what is profit function? Profit function is revenue minus cost. Now, what is your revenue function? See, this is your amount of production, okay? Amount of production. So you are producing Y units, okay? And you are selling each unit for P, okay? So your revenue will be PY. And what is your cost, okay? The cost of 1 unit of labor is W. W is the wage rate. So W into L plus the cost of 1 unit of capital is R. Okay, so that is the capital is R, so that is RK. So this is my profit function, revenue minus cost. So that is P into FKL minus WL minus RK. Okay, now if I want my profit to be maximum, okay, for maximum profit, for maximum pi, I want the partial derivative with respect to K to be 0, and I want the partial derivative with respect to L should be 0. So if we look at the partial derivative with respect to K, P is a constant because it is the selling price per unit. Let me differentiate F with respect to K, okay? And then WL, its derivative with respect to K will be 0 minus R will be equal to 0. And then when I differentiate pi with respect to L, it will be P into partial derivative of F with respect to L minus W equals to 0. So I want my rent to be, selling price into the partial derivative of F with respect to K. And I want my wage rate to be selling price into the partial derivative with respect to L. What do you mean by partial derivative with respect to K? Partial derivative with respect to K means how much, how much the production will increase when I increase the capital by 1 unit. And what do you mean by FL? FL means how much the production will increase if I increase the labor by 1 unit, keeping the capital as constant. So this is how we get a relationship between. Now, I don't know whether it is a point of maxima or minima right now, because we are dealing just with necessary conditions for maxima or minima. Okay, so let's see. We can have one more example. So consider a special case of the previous model. So now my production function is FKL equals to 6K per half L per 1 by 3. So now this is my P, this is my R, this is my W. So my profit function will be, so P into FKL minus WL minus RK. So pi KL will now be, P is 0.5 into 6 K power half L power 1 by 3 minus W is 1, okay, into L, and minus R is 0.1 into K. So pi KL is equal to 3 K power half L power 1 by 3, okay, minus L minus 0.1 K. This is my representation. Okay, now let's look at the first order condition. First order condition means necessary conditions for maxima minima. Then my pi K will be 0 and my pi L will be 0. Let us calculate pi K. So 3 into half K power minus half. I am applying the power rule of derivatives on K, keeping L constant. L power 1 by 3 minus 0.1. This should be equal to 0. Okay, so I'll have 3 by 2 L power 1 by 3 upon K power half is equal to 0.1. Okay, so I have L power 1 by 3, 3 times L power 1 by 3 equals to 2 by 10 K power half. So I have 15 L power 1 by 3 equals to K power half. Okay, so let's try to go to the second one now. Pi L equals to 0. So what is pi L? So pi L is now going to be 3 K power half into 1 by 3, L power minus 2 by 3 minus 1 equals to 0. So 3 and 3 cancel. K power 1 by half divided by L power 2 by 3 equals to 1. So K power half is equal to L power 2 by 3. This is my equation number 1 and this is my equation number 2. Use 2 in 1. So 15 L power 1 by 3 is equal to L power 2 by 3. So 15 is equal to L power 1 by 3. So L is equal to 15 cube. That is my value for L. And now I can calculate the value of K also. So how do we calculate the value of K? So we know that K power half is equal to L power 2 by 3. That means K is equal to L power 4 by 3. So we are squaring. So 15 by 3 power 4 by 3. So that is 15 power 4. So these are the units of capital and labor which are going to give me the first order conditions for maxima or minima. Now we can have maxima at these points and we can have minima at these points. For this, we will be needing the second order conditions, or we can say we will be needing the sufficient conditions. But this is a message to all of you as to how to apply the first order conditions to get the feasible values of X and Y, or the input variables, for example, K and L in this particular case, to decide the points at which the local maxima and local minima are going to occur, because we are going to get interior points. We cannot exist on the boundaries for local maxima or minima. So see you in the next class, where we will be discussing more on optimization of a two variable functions. Thank you very much.